Good afternoon and welcome everyone to our Thursday CREECA lecture series. Thank you for joining us this afternoon. My name is Jennifer Tischler and I'm the Associate Director of CREECA. For those of you who might be with us for the first time, I'll mention that there is a sign-up sheet that will be circulating. Please, we just need to have kind of a head count for our funders at the U.S. Department of Education. But if you do want to join our mailing list and find out more about upcoming events and funding opportunities, please give us your email address. And I'm not sure if this is on. Okay, now it's on. Okay, sound check. Is that okay or is that too loud? Good. Okay, it always sounds too loud to me. Maybe I'll just back up a little bit. Okay, so again, this is the final, the last of our regular Thursday talks, but not our last event of the semester. Next week on Tuesday afternoon, the Center for East Asian Studies has organized a timely event, the title North Korea's Involvement in the Russia-Ukraine War, a panel discussion. And that will be Tuesday, December 10th at 4 p.m. in this room, Ingram Hall 206, co-sponsored by the Center for East Asian Studies and CREECA. And the speakers are David Fields from the Center for East Asian Studies, John Hall from History, Yoshiko Herrera from Department of Political Science, and moderated by Kevin Kelly in the law school. And we have some copies of the flyers in the back of the room. So please do check our website, creeca.wis.edu, for upcoming events. We will soon be getting the spring 2025 lecture series schedule posted. I can tell you that our first speaker in the spring semester will be Professor Jeff Durham from the Department of History at UW, and we will begin on Thursday, January 23rd, 2025. But I don't want to break away. So now I'll ask Professor Volker Radula from the Department of Forest and Wildlife Ecology to introduce today's speaker.
Hi, everyone. I'm Volker Radula, faculty member in Forest and Wildlife Ecology, and I had the great honor to be a PhD advisor for AFA. So that's why I'm the one doing the introductions here. AFA is from Azerbaijan, from the Caucasus. Her family has deep roots in southern Azerbaijan, close to the border of Iran. She got her first degrees, her bachelor's and her master's at Baku State University, and did so well that they hired her as an instructor right away. Her degrees were in ecology, but then she gave courses on what is called geographical information system, computer maps, and so forth. That was followed then by a postgraduate diploma in wildlife conservation from the University of Oxford, then back to Azerbaijan for a while, where she worked for IDEA, a conservation NGO, also being very much involved with on-the-ground conservation efforts, but starting to map wildlife habitat, critical areas for biodiversity, which are themes that you will see in the third part of her talk today. And then she came to Madison. I did not mention temperatures and climate and anything like that. So no. But joined our PhD program and did excellent work then on the questions of land use change, which in the region of the Caucasus, with the collapse of the Soviet Union and the changes that happened afterwards were very rapid. She pioneered analysis of spy satellite data, and she will show some of that in her work also. And that work has been published in the journal Remote Sensing of Environment, which is the top international journal in the field. And then other work is in submission and in review and in other journals. So she's been very productive also as a co-author on several other publications. And in her work, and I think that's in a region like the Caucasus, really laudable, reached out to scientists from all the countries, Georgia, Armenia, the Russian Caucasus, and so forth, to co-author papers, work together on these questions, which are, of course, shared issues in all of them. She's also a great musical talent. So I've had the pleasure to hear her play the piano and sing. That's not going to be part of the talk today, I'm afraid to say so. But if you meet her in other settings or so, you may want to prompt her on that. So with that, it's an honor and pleasure to introduce you, Afag. I look forward to your talk. Please join me in welcoming her.
I'm very flattered. Thank you everyone for coming today. Okay. It's a privilege for me to be here to present my work here at UW, and tonight I'll be talking about an intersection between history and technology and conservation science. I'll talk about how we can use high-resolution satellite imagery to map the land cover and to understand changes in land use and wildlife habitats in one of the most culturally and naturally diverse regions, which is the Caucasus. So I will first give an introduction of the land use history overall, and then give a brief introduction to the remote sensing and how we use it in our field. I'll talk a little bit about Corona satellites, and which were the US-based spy satellites, and I'll introduce the Caucasus region, and we'll talk about our findings in land change and habitat change. The way land cover on Earth looks today highly depends on the decisions of our previous generations, and our decisions will likely have similar effects in the future. While land use on Earth has a very long history of many, many centuries, it has accelerated over the past century because of technical advancements. For example, large changes happened after the mid-20th century, specifically after the World War II, which is, if we look at this graph, we can see that human population grew rapidly here, and the magnitude of growth here is quite unique. The birth of baby boom population, who also grew to be adults in the 1960s, also brought in the demand for food supply for that generation and prompted the Green Revolution, which started about in the 1960s globally, meaning major agricultural advancements, which increased crop yields and food production and was actually pretty successful in mitigating hunger, but it also had negative effects on the nature and overall environmental degradation. Often irrational agricultural intensification can lead to the degradation of soils, of the rivers, and can bring the problems in wetlands and lead to the loss of natural ecosystems. Imagine going back in time to where the dams were not built in the rivers, or where the forests were not touched by humans. As scientists, we don't have a time machine, but we have the next best thing, which are the satellites. Often to look at changes in the land cover, so whether there was any forest loss or forest gain, or any growth in urban, like in cities, for example, we as scientists use satellites in our land change studies. So these are the series of Landsat satellites, which are launched and managed by NASA. So here's the year that they were launched, and then the years that they were active for. So they are actively capturing the images of the Earth. And here I want to show a very short video of how they are circling around the Earth and capturing every inch possible. So this is specifically the Landsat satellite. And in about a couple of hours, it makes one circle around the Earth and then proceeds to capture it further until it's fully captured the Earth within about 16 days, specifically for this satellite. Oh, did it stop? Okay. And what we would get from that is a satellite image, for example, this image over Madison, and we can actually look at those images, for example, this image of 2000, and then this image of 2024, and look at the changes that occurred between those years. So you can see some new buildings pop up here, and then you can see some of the fields here. They got also changed. They're now also buildings, quite a bit of urban sprawl here. So we can see how much has changed within 24 years. And there's a bunch of other satellites and way more than depicted in this graph, which capture imagery in higher resolution, but starting in after the early 2000s. So if we come back to this visualization, we can see that we can successfully assess changes. Sorry, my mouse keeps moving here. So for example, we can use the data from here to compare it to data from here. So basically we can assess changes continuously through a very long time over the entire planet pretty much. But the studies that often look at land changes, they date back to 1980s because that's when the Landsat data is available, and usually it's the easiest to access and available to use to analyze. So we're missing the time where the global changes that we just talked about, which are the Green Revolution, population growth, we're missing that time that happened before the 1980s. In addition, in that era, the United States and the Soviet Union, the two large powers of the 20th century, they were in the middle of the Cold War, which actually fueled the space race between them. And one of the successful outcomes of that race for the United States was the launch of Corona spy satellite series. It was launched in 1959. Okay, let's do something fun here. Using the Cold War era as a hint, does anyone want to guess what is the structure that you can see in this image? So this is the Corona image from 1964, and this is what the structure looks like right now. So it's abandoned, but what do you think this structure can be?
Some kind of missile site.
Exactly, yes. So that was the main aim of the Corona satellites. They were mainly aimed at capturing the missile launch sites of the Soviet Union, and this is what the plan looked like. Yes. So, but in addition to capturing its main goal, it also captured the state of environment at that time. Corona was the code name of the satellite, and it actually comes from a Slavic word, corona, which means, yes, it means a crown. And mainly the reason for that is that they were aimed to be located above the Soviet Union and capture, mainly, like meaning capture the Soviet Union. So that's where the name comes from. The same reason for the naming of coronavirus, because of how it looks like a crown, which made it super challenging for me to do literature search after the coronavirus. The process of bringing the corona data back to Earth is also fascinating. So the capsule, after capturing the imagery, the capsule would actually eject off the satellite and be sent towards the Earth, dropped towards the Earth. And as it approached, the parachute would go off, and the Air Force, they were called star catchers, would actually capture them mid-air. To get the capsule here. So I'll show in a little bit. better quality. Here it's size in relation to me. It's held at the Smithsonian Museum in DC, and that's where you can also see it. So this is where what that capsule looked like. So they would capture it mid-air, and 99% of time they were successful in that. While the Soviet Union and its surroundings were the main focus of Corona satellites, they also captured extensive images across the globe. So when in the 1990s, Soviet Union crashed, there was no more need to keep the Corona data a top secret. So in 1995, President Clinton declassified the scientifically or environmentally useful imagery acquired by these satellites. So we could then use them for science. While the Corona data becomes more and more used and known, it has not been used very widely yet. This is where the Corona images are stored. They are in printed versions, and this is in the United States Geological Service Center in South Dakota. And when we order these images, they scan them and then send us basically black and white online TIFF image strips. So after we receive them and we locate their correct location on the Earth, we can then check them out. So this is what they look like. The brilliance of Corona data is that although it was captured over half a century ago, the resolution is so high, it's 1.5 to 3 meter resolution. These images that I'm showing here is 2.5 meter resolution. So it's very high resolution. And for example, like you can see crop fields pretty well, lake, and the grassland, the forests, but also look at the urban area. You can see the buildings in very good detail, which is pretty fascinating. I actually spent hours looking at them, especially at the areas that I'm familiar with, to see what the area used to look like and how it has changed. And it's the amount of changes is immense. To look at the changes in land cover and their effect on the habitats of wild species, I chose the Caucasus as a study area. It's located between Europe and Asia, between the Black Sea and the Caspian Sea, and it covers approximately 250,000 square kilometers, which is about 1.5 size of Wisconsin. But it's highly diverse in elevation. It ranges from -27 to next to the sea to over 5,600 meters above the sea level. It has a high variability in terms of precipitation and climate, biodiversity, and it's important as a migratory path for many wild species. For many centuries, livestock production and cropland cultivation has been an important part of the local economy, but being strategically located between Europe and Asia, the Caucasus has always been part of an empire that existed in the region. So in the 1200s, it was the Mongol Empire. In 1600, it was Ottoman Empire, which is now mainly Turkey. In the 1800s, it was the Persian Empire, which is now mainly Iran, current day. And in the 1900s, it was the Russian Empire. But for the most of the 20th century, the Caucasus was part of the Soviet Union, and it experienced various land initiatives that the government introduced. So during the Soviet times, it was the Soviet policies, and after the Soviet Union crashed, each country that was in the country, in the Caucasus after its collapse, they had their own divergent policies, which also affected each country's land cover in a different way.
So it comes with no surprise that land and nature in the Caucasus is shaped by political changes and by policy changes. And what made it interesting for us are specifically the changes that it experienced in the 1960s, which we can then look at with the corona data. Let's look at another then versus now image. So the corona image on the left, and this is the current image. This was also on the poster for today's talk. I'll have two questions. First question, what's the difference you see between these two images? And my second question will be why? But who wants to guess?
Are there more buildings, or is it just that the detail is better?
There is a little more buildings because given the time, change in time, yes, that's one of the changes. And if we look at the cropland, do we see?
More crops now, right?
Yeah.
More of a farm.
Exactly. So it looks like it's very patchy right now, while it used to be one crop field in the Soviet era.
Oh, so individual farms instead of collective farms?
Exactly, yes. Thank you. Yeah, so it used to be collective farming where inhabitants of the village would invest and work at the collective farm together during the Soviet times, while after the Soviet collapsed, they distributed the land among the population inhabiting the village, the region. So
Is there any reason why the illumination is so different?
it depends on the time of the day.
Okay.
It depends. Do you mean like the contrast of the image, or like how the
Well, the way the buildings stand out so
Yeah.
much more clearly in the right image.
it may be also a little higher resolution. It's current Google Earth imagery,
Okay.
while this is pretty high resolution to see the buildings, but not as high as the current Google Earth imagery.
Okay.
Okay. So even we can see here on the left side, the collective farm was actually dissoluted during the Soviet times already here. And we can see that change in the imagery here. Today, I will not go into technical details of how to classify corona data, meaning making land cover maps using corona imagery, because I prepared this presentation for non-technical audience, but you're welcome to, we've published the methods, and you're welcome to read through if you're interested, and reach out if you have any questions or research ideas. But I want to show the final map that we derived using the automatic machine learning approach and using cloud computing. And this classification is for full suite of land cover classes, meaning the forest, grassland, cropland, barren, wetland, urban, water bodies, and snow and ice. In addition, my former lab mate Johanna Buchner, as part of her PhD, published a series of maps for the Caucasus using the Landsat data, so after the 1980s, which then we used to assess the changes between 1960s and current day. Given that the Soviet Union collapsed in the early 1900s, in order to find changes since then, we combined our 65 map with 87 map to look at the Soviet era changes, 87 map with 15 map to look at post-Soviet changes, and then 65 with 15 to look at overall changes through the entire time. So here are the resulting 3 change maps for each era. We derived a bunch of change classes. I want to zoom into a couple of examples here to highlight the importance of the corona data. For example, here in Georgia, if we only look at changes 87 to 15, then we see cropland abandonment. So here, this brownish color is cropland abandonment. So we see a lot of cropland abandonment here, captured here. But then if we only study this time period, then we think that there was a lot of abandonment, and we cannot tell what was the reason for that. But then if we add the 1965 baseline to it, then we can see that these were actually the new croplands, so cropland gain, which is the pink, which were mainly often based on our study, the areas that may not be very suitable for agriculture, but maybe they were plowed actually because of government subsidies, and maybe they were not suitable for machinery to get to, specifically in this mountainous area. While other areas which were more suitable to agriculture, for example, here in the south of Russia, they were plowed before the 1960s, and they remained plowed both in the post-Soviet era, in the Soviet era and in the post-Soviet era until today. And then another example here from the south of Azerbaijan, we see that the new center pivot agriculture appeared in the former grasslands. So this circle. So between 65 and 87, we see mainly stable grassland, but then they appear after the Soviet collapse. And we also see that in the 50-year change maps. Overall, we found that the forests were lost during the Soviet era, but then they regained after the Soviet collapse. And similar to the maps that we looked at previously, if we only look at the Landsat data, then we see a lot of forest gain. But we do not see the forest loss that happened actually before that, which then regrew back after the cropland abandonment, for example. So we may get a wrong impression unless we add the corona baseline to our study to look at the reasons for a lot of the land changes. This is a great example of a shifting baseline syndrome, which means that limited or missing information of past conditions result in gradual change of our understanding of the past. And for example, in this photo series, all these fishermen seem happy about their catch, but they probably wouldn't be as happy if they knew what the previous generations caught before them, 20, 30 years before them. Same I can remember from the city I grew up in, for example. When I was a kid, it used to snow quite a bit, and now it may snow once in winter and melts right away. So if I talk about my childhood, my baseline is my childhood, but I'm sure it was different before that. So it would be interesting to see how this baseline shifts. So as in our case, by extending baseline further back to the corona data, we found strong differences in magnitude and directions of land cover during and after the Soviet era. So with corona data, we can extend the studies back further by at least 20 years, which is the time that's important for regions, especially such as the Caucasus, which experienced large changes during that time. And that would be also relevant to many current countries that were part of Soviet Union, or they experienced the effect of policies of the Soviet Union. Now let's talk a little bit about wildlife. When we have the maps of land cover, we can then use them to map habitats, to look at the habitats of wild animal species, and also extend the baseline of their habitats back in time. For example, we studied large mammals, and for them, it's especially important because their lifespans are relatively long. So it takes longer for them to recover their populations and it can take decades to correctly assess the loss in their habitats. This can cause extinction depths, which means that future ecological cost of current habitat destruction, because it can take many generations before the population gets extinct. So after the habitat loss, it may take 20 years until the population gets extinct, while we could already mitigate the loss of habitat and prevent that extinction or prevent the death in future. Let's have a little more fun here with the imagery and look at some potential causes of habitat fragmentation, habitat loss for species. Let's look at this image here, and then probably this is pretty obvious what's happening here. Does anyone want to guess?
Open pit mining.
Exactly, yes. Thank you. So this is what it looks like on the ground, and similar mining has occurred in Armenia here over time, and all this causes habitat fragmentation and disturbance to animal species. So even roads or leading to these mines can create fragmentation for habitats of the wild species. And then let's do one more here. So we see I'll give you a hint. The main difference here is the river. What's happening in the river? So here, this river, the flow is slightly different.
Is it wider and channelized? Was there a dam?
Yes, it was a dam construction, and it started in 1976, so it wasn't there during the Corona era, and then they actually reinforced it in 2008 also. So here it's the zoomed version of it. The main reason was, of course, to get the electric power, but also they were the river was flooding the town here. That it was flowing through, so they decided to redirect it. Okay. And then the same reason here, it's the dam construction. This is in Turkey. The construction occurred in late 1990s. And then also other reasons for habitat fragmentations are growth of human population. So here we see the growth of urban area quite a bit in Azerbaijan, and agricultural expansion. Unfortunately, the Caucasus is considered one of the 36 global biodiversity hotspots, meaning that it has lost a large part of its biodiversity, but it still has rare ecosystems and endemic species of conservation concern. It covers several global biomes, and it's so far still very diverse in fauna, with over 400 bird species and in general over 800 animal species. And again, I wanted to revisit the area changes here. Although overall for the study area, the land cover was pretty stable, but the amount of change that occurred between the classes, it has affected the habitats of wild species quite a bit. And so we were interested to see how it has affected the habitats in the Caucasus. Specifically, we focused on this ungulate species, Bezoar, chamois, gazelle, West and East Caucasian tour, roe deer, red deer, and mouflon. 6 of the species, so all except for the East Caucasian tour, they are at least in red books, in red lists of at least one country in the Caucasus. And then these are all ungulate species of the Caucasus, except for the newly reintroduced bison and very widely spread wild boar. So here's the presence data available for our species. These are the points where the scientists have captured the species, meaning they have seen the individuals or tracks of the individuals in the wild. And the overlapping grayish patch is where the corona data is available. So that's the study area where we will do the habitat change analysis for. And again, using the maps for several time steps, now we're also adding the 2021 map. And then overlapping it with the presence data, we want to predict what are the suitable areas for the species to inhabit. So basically, we overlap these points with all the environmental factors. For example, precipitation, the mean annual temperature, mean annual precipitation, ruggedness of the terrain or slope, like what is the angle of the slope, and the proximity layers, such as the distances to water bodies, which would be the water source for species, and shelter, which is the distance to cliffs. So we overlap these points with the satellite data, and then we capture, for each point, we capture the value that corresponds to each of these variables. So then when we get for each of the points for the species, we get this data. We then can model the habitats that are suitable for the species. So for example, this point, let's say here, the temperature, mean annual temperature is 16 degrees. There is low precipitation, and it's not very rugged. So it will, the algorithm will say that on average, the gazelle species who like to live here, they prefer about 16 degrees Celsius. They prefer to not live in mountainous areas. So based on that, it will tell us what are the other areas that are similar to what we see based on these points. Yes. Thank you for the reminder.
Project is ongoing.
That's true. So actually, these are the results that I got this week, and these are very fresh, as you can tell. So this is what we get in the end. For example, this is for red deer. What we see is highly suitable areas. Like everything in gray is considered non-habitat for them, but then highly suitable areas are in the mountains here. And so it's highlighting the areas that are based on these environmental factors are also similarly suitable for the species. So let's look at the changes in their habitats. For some species, for example, for mouflon, we see the decrease in overall suitable habitat. So everything that's in green is suitable habitat, and we see the decrease over time. Then if we look at roe deer, while it looks like the habitat is increasing, so we see that green is becoming larger, but we can see that the dark green, which is the highly suitable habitat, is actually decreasing as well, which means that the high quality habitats are actually decreasing over time. And actually, we found that habitats of most mountain species decreased, and that may be due to the forest loss that we observed earlier, especially in the Soviet era. And that often occurred in the mountains. And then if we check the numbers for the gazelle species, which is the only non-mountain species, lowland species, then it seems like there was a gain in their habitat. But if we look at the maps, we can see a lot of the shifts in their habitat, which may be related to the abandonment of existing and establishment of the new croplands in the lowlands, especially gazelle live in the lowlands of Azerbaijan. So there was a lot of shifts between grass and croplands in the lowlands of Azerbaijan. And then we can also look at the protected areas, so like national parks, reserves, and sanctuaries, and see how successful they are in preserving the wild habitats. We examined the net changes in these protected areas, and we found that strictly protected areas tend to be more successful in conserving the habitats of wild species. Having said that, we can't expect an immediate positive effect as soon as the protected area was launched, because it takes time for the habitats to recover. For example, here in Gögöl National Park, which was a reserve in the Soviet era, so it's a strictly protected area. It was established in 1925. The red deer was not present in the 1950s, so they started the reintroduction project back then. And fast forward to 2021, it seems like it's there are a lot of highly suitable areas, which are in dark green. And also based on a recent study here, the red deer populations are actually currently also growing in that Gögöl National Park. So as implications of our study we're presenting here is that we can use the 1960s data for land and habitat management today, and that will help us in reducing the shifting baseline syndrome, and specifically for the Caucasus with diverse policies in the countries, it will help with cross-boundary conservation efforts. And specifically, our results for the protected areas can help inform plans for ongoing plans for creating new protected areas and expanding the existing ones. And also hopefully for future prevent the species extinction. You have now seen this image quite a few times through my presentation, and I'll tell you why I shared it. This is the region where I'm from, where my parents are from. It's in Azerbaijan. It's called Gubadlı. So the Caucasus is very close to my heart, and I've been very fortunate to be involved in conservation projects in the Caucasus. And it's fascinating how, despite all the political and economical changes, how the nature is resilient to the human intervention, and if given a chance, it may have the ability to recover. So as you live here today, I encourage you to think about our choices as society and as individuals. Thank you so much for your attention. I'll be happy to answer any questions you may have.
I'll just bring up the lights so you can see. Are you okay handling your own, calling on people yourself? You don't need a moderator, do you?
Sure.
We're a friendly crowd.
Yes. Hi.
Yeah, thank you so much. Very interesting. Two questions. One very small question, which was just, how come there was some missing spots with the corona data, like the squares of it. But the